Hello and welcome to this fireside chat optimizing HPC manufacturing and life science applications to maximize your supercomputing results, brought to you by HPE and AMD. In this informative session, you'll learn more about HPC collaborations that can benefit your next supercomputing project. In this fireside chat format, you'll hear how HLRS, AMD, and HPE have collaborated to solve problems in engineering and life sciences applications, as well as the benefits the HPC community will see from public-private collaborations in supercomputing. I'm Addison Snell with Intersect 360 Research, and with me today on this panel, I have Bastian Kohler, who's the Managing Director at the High Performance Computing Center in Stuttgart, or HLRS, Raghu Nambiar, who's the Corporate Vice President of Data Center Ecosystems and Solutions at AMD, and Bill Manel, the GM for High Performance Computing at HPE. Thank you all for joining me on this panel today.
Yeah, thank you, Addison. And thank you all.
Hello. Thank you, Addison. Thank you, Baston and Bill. Great to be here.
Hi all. Good to see you virtually.
And Bastian, I'm going to start with you to kick things off here, because at HLRS, of course, you support a very wide range of high performance computing or supercomputing types of applications. And on your Hawk supercomputer, which is now pictured behind you, your new supercomputer, in particular, I know you're solving the needs of a lot of your industrial partners with scientific but engineering types of workloads and life sciences types of workloads that your industrial partners are interested in. Can you talk a little bit about the breadth of applications that HLRS has to support and how you're using Hawk to help support that community?
Yes, sure. So we have mainly a focus on, as you already said, engineering and life sciences. This is one part is, let's say, our duty as a federal center, and let's say we had a good split up between the centers here. So if we look at the different domains, especially in the engineering sector, we have a lot of automotive stuff ongoing here. We have some medical activities, and with the life science, we also explore a new field, which is called global system science, where we really work with politics, society, and especially currently with this COVID pandemic around there, we have some nice application areas of this way, where we can really go from really baseline research on the virus itself up to societal questions and challenges there. Also, with, let's say, the engineering part in the automotive sector, we explore with them the new fields, and this is where we can really make a good use of our new flagship system, which you see obviously behind me. And we are looking forward really to see what is possible with that.
What I really like about this is it's sort of a microcosm of the HPC industry to see this entire breadth of application. Now, maybe one individual high performance computing user doesn't have that whole range of applications, but Bill and Raghu, when you're talking about the whole scope of applications that your customers are running, you've got to design to meet all of these different types of requirements. Bill, do you have, I mean, what do you see there among your user base?
Yeah, certainly. It's very common for us to have sites like HLRS where they're trying to serve a very wide and diverse user base, many applications, thousands of users at any one time. And in the case of HLRS, it was a competitive procurement, so there were some specific benchmarks we wanted to hit, and so we used that to design a particular system. But I'll have to say that with this particular system design and the Apollo 9000 that it's based around, we're able to give very good performance for a wide variety of applications versus, in some cases, you might see systems that maybe run a single workload, or maybe a small set of workloads, like in weather, where you're much more focused on that particular workload.
And Raghu, how about your perspective from AMD about the breadth of applications that you're supporting?
Yeah, first of all, I appreciate the strong partnership with HPE and HLRS. From a workload focus perspective, especially in the HPC space, it is very much in line with the workloads that Baston and Bill just mentioned.
Yeah, I have to note that, when HPE was designing the system for HLRS, we, certainly had a variety of different solution elements we could choose. And it was clear from the performance we were seeing with the AMD Rome processor that they clearly were the choice. And yeah, again, appreciate the hard work that both performance engineers on my side and performance engineers on Raghu's side put into making sure we had the best solution for Bastian and his team.
I actually was just about to drill in on that, Bill. We're talking about this Hawk system at HLRS. It has over 700,000 cores. It's a 26 petaflop system, and we were just talking about the breadth of applications it needed to support. Now, you've talked about Apollo and the EPYC Rome processor. How did you work together with Bastian and HLRS to determine the configuration of this particular system?
Well, certainly, we looked at the benchmarks we wanted to run, and could get some kind of sense in terms of what performance we'd want, what would be the particular SKUs we wanted to use, and again, we actually bid this earlier before Rome was available. So on both sides, we had to make some estimates, and certainly work closely together on that to understand the architecture and how that architecture might be projected against some existing processors, the Naples processor, and be able to come with the right performance projection. But it was again, that's one of the challenges when you're bidding something that's not going to come out for a while, it's not done yet. You have to do that work, and it's really part of the science that the performance engineers, working closely together, have to be able to accomplish. A little bit of art and science from that perspective.
Now, Bastian, HLRS is notable as being at the forefront of supercomputing capability. And you had a previous system, Hotzelhen, where you supported these types of applications, but you've had a tremendous performance gain now available going from that previous supercomputer to Hawk. Can you talk a little bit about what that performance gain means? Not just in terms of something raw or abstract like petaflops or number of cores, but in terms of real application capabilities, what it means for a life sciences application or an industrial simulation to have that level of capability.
Yeah, sure. So it's quite interesting usually because we already see currently also demand for new system, as we said for the old system. We usually have some bets how long it takes to have the system full, and let's say our users are quite good in making maximum utilization of the system. So first of all, we always know there's a need for getting bigger system, or let's say an improved system in terms of the capabilities which you allow for. So if we look at our engineers and coming from the industry, they have certain interest also to understand, let's say, what is the ratio between, let's say, sizing up the problem space, time to solution, and all the stuff. And we see a good ratio here for them. So they can, let's say, dig deeper into the problem space and really increase the maximum output of that, also in terms of quality. Now, looking at, let's say, machine learning attempts, etc., they also start using them. They can do much more test training of the system. And by that also, the time to the solution gets much better. For the life sciences, and especially what I said, these global system science, it's very interesting because we see here that we will get a demand of coupled simulations. So really big simulations running in parallel, where you don't have, let's say, the old possibility of saying, okay, there's a center at A and a center at B, and you transfer the data between them, and one takes the output data of the other one as an input. So really, we need to run those workloads on a one system. And this is especially important for us, because if we look at these kind of societal challenges, and with one example is the migration movement, there's a lot behind this. It's a climate part, it's an economic part, it's a societal part in terms of, let's say, reproducing data, which is in there. And if you would do this, let's say, distributed between different centers with different machines, this takes quite too long for the decision takers to get the input here. And that's for us also that we see there's much more potential than just scaling an application up, but really increasing the impact of the application by putting a lot more properties together and parameters that were able to do before.
Yeah, I'm really glad you brought up machine learning or artificial intelligence, which is certainly a major trend we're seeing in high performance computing. I'd like to cycle back around to that in a few minutes, but just staying within the envelope of scientific and technical computing, you're talking about what I love about this industry is that there's always a tougher problem to solve. Yeah, you're always fitting your constraints to what are the capabilities that you have, but you can add more degrees of freedom or more fidelity into a model. And it seems like we're always chasing new levels of capability. Raghu, that's what drives new levels of performance in processors generation after generation, right?
Yeah, absolutely. If you look at AMD, as I said before, we are really excited to partner with the HPE and HLRS in providing high performance and high efficiency. If you look at the deployment at HLRS, it is powered by our second generation of EPIC CPUs, 7 nanometer technology, offering up to 64 processor cores and high memory bandwidth and high memory capacity, optimal for a variety of applications that we have just discussed. Another key point to note is that HLR supercomputing Hawk cluster, they're using a 200 gig network connectivity that is enabled by PCI Gen 4, that is unique in AMD's architecture, and first to bring a PCI Gen 4 to market in the x86 space. Again, high performance, high efficiency, that's what we are bringing on the table in the HPC space.
Bill, talk to me about these advancements in scientific and technical applications.
Sure. Certainly as we continue to march forward, we've traditionally HPC has been traditionally around modeling and simulation. We're trying to model the real world and then be able to predict behavior. For example, how is this car going to react when it crashes into a barrier, for example. And so as we go forward, that's certainly important, and we're doing more. The performance we have in the systems that, like Hawk, that we're deploying allow us to do a tremendous amount of simulation. So we gather a tremendous amount of data from that, and then at the same time, it's sort of an interesting outcome of that. Is that you end up with a lot of data, and then you can actually apply more standard analytics on top of that data. So in other words, you got many runs. Okay, what do standard analytics apply to those various runs in terms of some of the results? What kinds of things can that tell you? And so you more and more see engineers starting to do that. And in that case, they're actually pairing more traditional modeling and simulation with more traditional data analytics, statistics, and these sorts of things. And again, getting more insights in terms of their data, which really was hard before because you just didn't have that the performance you needed to gather all this data. But now that you do, and so that allows another vector into, as an engineer, as a scientist, to actually understand your problem and handle things like fatigue, for example, for in mechanical design and these kinds of problems that become easier now with some of the new techniques and the performance capabilities of the systems and obviously the chips that AMD is producing at this time.
Yeah, that really sets up the next major topic for this discussion, which Bastian also referenced with regard to machine learning, and now you're talking about analytics, is analysts tracking high performance computing. When I look at the last decade, the biggest thing that happened wasn't the expansion of the technology set, it was the expansion of the application set. Because in the first part of the decade, we had this whole wave around big data and data science and data analytics, and that was transformative in terms of the workloads that we would see in high performance environments, particularly in the commercial sector of high performance environments, but also affecting these large scale supercomputer centers. And now with machine learning and artificial intelligence, we have another wave of how these applications are evolving. And what I'd like to talk about is how these are not distinct, but how they're working together. How do you see analytics augmented high performance computing or AI augmented high performance computing? And, Bastian, I'd like you to start by talking about how you're seeing that at HLRS, and then maybe both Bill and Raghu, you can jump in after that, talk about analytics and AI together with HPC.
That's a good point. I remember, I think some years ago, myself and Michael Resch, the director of our center, and a colleague, we wrote a paper where we said, okay, it's nice, you have, let's say, HPC, and we were already quite, let's say, futuristic, saying, okay, there's a second part, which is HPDA, so high performance big data. And we even said, okay, there might be a missing link, which is the artificial intelligence in that regard. And if we look at this coming from that background, what we did is we structured a European Center of Excellence on engineering, which is currently running. It's currently a funded project, but should work into, or let's say it should be moved into a sustainable activity. And the interesting part here is we always started to look at the life cycle of engineering workflows. And this is not the plain scientific one, but we have a lot of industrial partnerships here. And we always looked at this, okay, the simulation itself, so the running of an application on a system is just a part of the whole thing. And then you have the data analytics to get, let's say, the results structured in your way. And then you do the AI, and then you feedback, let's say, potential results back into the simulation. And this improves a lot. But still, this was always a very cost-effective, intensive part if you looked at, let's say, running this on smaller systems, because then you need a lot of capabilities there and performance here. And now the bigger the systems get, and the better, obviously, also the applications get, which is somehow going hand in hand. The bigger the systems are, the better you can improve your applications and better make use of new features, of new technologies. So this also HOG is one of the systems where we said at the end, the set together of the system and the design of it really gives us the feeling that this is exactly what we need to enter this, let's say, multi-X workflow, or to cover really the whole life cycle of a simulation, not only going into the simulation part. I put in input data and I get some output data and do some plain calculations in between, but really making much more complex and thus more effective.
Yeah, and I would add, when I was in the aircraft industry, quite a while ago, there used to be a very long process. First off, you design your engineering model, if you will, for the aircraft you were doing, and then you always had your we call it the control laws model, which is basically how the air works and so forth around that. And then you tested that, so you actually had to fly the aircraft itself to gather all that data and verify your model. And then once you had the model verified, then you would feel confident enough that you could start to push the boundaries of that model, and actually test further along the envelope. So not until you really understood would you risk the airframe and the crew in doing that. And so with a lot of the work we have today, it really shortens that time frame for doing that work, because before a flight test program could be literally years in the making when you look at, doing your models and then doing your flight tests and comparing your results, and maybe you guys actually have to fly some more and things like that. Now you can really compress that development cycle down, because you've got the ability to generate lots of data and verify that back. And then on top of it, if, for example, you can use perhaps either an aircraft already in the fleet, similar aircraft in the fleet, a similar engine, then you can start feeding data in as well and checking your model against actual data in flight if you will, as you're developing your model. So it all becomes what I was talking to a small jet engine manufacturer about a year or so ago, and their next jet engine that they're coming out with will have 5,000 sensors on it. So now, the engineer, as they're developing their model, can now take advantage of practically real-time data and be able to get a better model. And again, it's all about making products faster, cheaper, and better quality and safer as we get out there. And I think a lot of the advances that we're seeing is allowing that to happen.
Yeah, so that's a very good question. I really like the question, and I agree with Bastian and Bill. When you look at the future of computing, right? I see three pillars, okay, complementing each other. First pillar is, you mentioned, big data and analytics. Okay. Second pillar is HPC. That's the core of this discussion. And third pillar is artificial intelligence and machine learning. They're fundamentally different from each other, but they can work together. So that is going to decide the future of computing. So if you look at the big data technologies, they are great for storing and processing large amounts of unstructured data. It can basically enable a data pipeline tier for collecting data from various sources, doing the data conversion, data integration, and data preparation for HPC simulations. Okay, and there are many well-known algorithms and simulations in HPC that can help train AI systems.
Bastian, while I have you here, I just need to talk about the breadth of applications you do have going at HLRS. We've been focusing mostly on things like CAE and life sciences, but of course, you're at the forefront of supercomputing here, and I, as a citizen of the world, am grateful for the work that you do in areas like medical research or designing smart cities, COVID-19, and how we combat that. Can you talk about some of the application areas that are in the scope of your research?
Yeah, sure. So we have one area is obviously in medicine, where we work together with some hospitals here to improve the implementation, or let's say to improve reconstruction of bones with hip implants, for instance, or bone implants in general, where usually it usually sounds quite tough, but a doctor usually take some sort of a bet on putting an implant in there, and then it works or it doesn't work, because he has a patient in front of him and he looks at it, and he does this by experience for now. What we've seen is that there are certain patterns in terms of, let's say, how the patient, let's say, the patient is configured, as we might say in the computer scientist world, in terms of what is his age, what is his gender, what is his, let's say, lifestyle, and things like the weight, etc. So every patient is somehow a bit different, but still you can cluster them in certain categories. And for us, the interesting part is really to design these implants in a way, and to set up some sort of an intelligence behind that database, so that the surgeon gets some sort of a support in terms of a decision-making database or supporting database to see, okay, this patient has this kind of properties, so it's better to use this kind of implant, etc. So make it just more sustainable for the patient himself. In terms of COVID, yes, what is interesting, as I said, there was this interesting and traditional way of understanding the virus itself, looking at the molecular dynamics world in terms of treatments, etc. But also here we go beyond this and then work on, let's say, a detection, or let's say to see how does it spread, and where does it spread. So we're working together here with the university in London to really detect this on a part of London, to understand the spread of COVID and get some feedback in terms of what could you do as countermeasures and stuff like that. And we even, let's say, try here also to get the data together, get understanding also of the patient treatment, then in the middle. So what was treated there, how does it work? What is, for instance, the utilization of the hospital beds, the ICUs, where do we get into a critical factor, etc. So you can do a lot of things around that, where you have to many cases to use, again, the combination of HPC and AI especially, and some data analytics to go in that direction.
Now, Raghu, the AMD processor elements, both CPU and GPU, have been gaining tremendous momentum across HPC and are highly rated by HPC users in terms of future outlook and planned adoption. You talked about your partnership before with HPE and HLRS. Can you talk about those partnerships and your own internal development in terms of building out the ecosystem for supporting these applications, what you're doing to build the ecosystem for the future of HPC with your processors?
So sure. So AMD is making a big comeback in the data center space with the EPIC series of processors and Radeon Instinct GPUs with continuous innovations and a strong roadmap, enabling software ecosystem, performance optimization, creating best practices, and delivering easily consumable solutions are part of a major investment from our side. If you look at today, we have a very strong software ecosystem of partners. We are able to demonstrate industry leadership performance and price performance through industry standard benchmarks. Today, we have 170 plus world records in the key areas, including HPC. Many of them are on HPE systems, thanks to Bill and team for joint engineering and collaboration. And HPC is a major area of focus. As you know, our engagements with the national labs and the research institutions like HLRS, but we are also working closely with the ISV ecosystem in commercial HPC space, creating differentiated offers in manufacturing, life sciences, oil and gas, financial service industry, and others. Other area of focus include software-defined infrastructure, virtualization, hyperconvergence, containers that is applicable across application areas. And we are also working closely with the open source community in innovating and joint optimizations.
Yeah, this is critical work with your ROCm open ecosystem. And as you pointed out, many of these areas are focused on independent software vendors, the ISV space, particularly in engineering dominated areas. Whereas if you go into life sciences, we do see a lot of open source, and other areas rely on in-house. So having that open ecosystem can be quite critical. And I appreciate the work done there. Bill, I'll wrap up with you here, because we've seen HPE is the leader in providing high performance computing systems, the worldwide leader by revenue for many years now. And that goes back to before HPE acquired SGI and then acquired Cray to really give you additional capabilities at the apex of the supercomputing market, where you're now getting a lot of wins at major national labs around the world. How does that level of supercomputing capability at the zenith of the market give you additional reach or benefits for the broader HPC ecosystem, from entry level up through mid range and high end? The complete worldwide HPC ecosystem. How does that benefit from supercomputing prowess?
Well, yeah, certainly. A lot of the more commercial markets are going to be a bit more conservative, so they take a little longer to transition. And so typically the work we do with HLRS, as an example, and Bastion are bleeding edge type activities, and certainly we have an opportunity to see how the technology works, how it works well, and how we can improve it. And then the next step for us is actually taking that technology and making it more widely available. And we've seen over this past calendar year a pretty significant migration of applications onto the EPIC architecture that Raghu was talking about, that AMD has been introducing. And I think that's in no small part to all this, let's call it pathfinding work that we've done already with national centers, with education, and university type customers, as well as some of the national labs in the various geos. And so see a big part of that going forward, and we actually, over the past year or so, have actually taken, some of the results that my team and with concert with Ragu's team have been able to show with some of these, not only engineering applications, but also EDA type applications, and take them to customers and say, hey, look, this is the kind of performance you can get versus what your more traditional type of processor and technology choices have been. And we've changed their minds in a lot of cases, and we've seen some pretty significant adoption across a variety of industries, financial services, engineering. I mentioned EDA. Even in some of the what I call sort of fringe HPC areas where performance is important, but they're not necessarily doing math. Things like booking, reservation type systems and these sorts of things. I've also seen the benefits as well.
I've been speaking with Bastian Kohler of HLRS, Raghu Nambiar of AMD, and Bill Manel from HPE, talking about the evolution of high-performance computing and artificial intelligence and the optimization of a wide range of high-performance computing applications, particularly in engineering and life sciences. Thank you to all three of you for joining me for this discussion today. I'm Addison Snell with Intersect 360 Research. Thanks for joining us.
Thank you.
Thank you very much.
Thank you.